So I'm continuing from my last video, and I'm looking to see if there's any way I can express theta or these arc cosine expressions in some kind of algebraic form. Or another option is to stick these things into Mathematica um, and make it just brute force it because it's got superior calculating capabilities. All right, there's our three functions. R is square root of x squared plus y squared plus z squared. Theta is arc cosine of z over square root of x squared plus y squared plus z squared. And phi of x, y, z is arc cosine of x over square root of x squared plus y squared. Okay, once again, I'm going to set up my Jacobian by doing some copying and pasting. It's going to be 3 lines, comma, dun dun, comma, dun dun. And actually, I should just make the first line first, comma, that, and we're going to go derivative r, derivative of theta, and derivative of phi. So that'll be one line, and then we're going to copy that whole line in here and here. This time, okay, and then I'm going to change this to y and this to z, this to y, this to z, and this to y, and this to z. And we're going to name this guy, why is there, oh, there we go. And we're going to name this guy Jake again. Jake is equal to that. And there it is. Actually, it ends up looking more compact. Let's look at the matrix form of Jake. Matrix form of Jake. Looks fairly compact compared to the other equation that I had. Let's simplify, see if what happens. Or no, actually what I want to do is matrix form Jake dot transpose of Jake, and see what comes of that. Let's hide something here. I don't need to see this over and over again. And, what's going on? I put my semicolon in the wrong spot. Okay, so Jake.transpose Jake, and what I'm going to do is simplify that. See if it comes out nice and neat like the other one did. Simplify Jake.transpose Jake, and it comes out like that. That is still really, really ugly. I think it is interesting that all trace of the arc cosine though has disappeared, and so there's actually no sign of like trig in there. So I'll look up derivatives of inverse trigonometric functions on Khan Academy. I can and sign up to save my progress. That'll be cool. All right, do I have what I need from the first 10 seconds of the video? Derivative, he says in the last video, he proved that d dx of inverse sine of x is 1 over square root of 1 minus x squared, which means I could just come back here to a previous video and check that out. All right, he gives one hint being try x equals sine y. So we've got theta equals cos inverse of z over square root of x squared plus y squared plus z squared. And we'll go ahead and take the inverse of that. Cos theta equals z over x squared plus y squared plus z squared square root. And then what next? We want, well, this would just be called f of x comma y comma z. So we'd have negative sine theta. Do I want to say d theta here? Equals del f del x dx plus del f del y dy plus del f del z dz. This is not what I wanted, I don't think. Although maybe it is, because sine theta is going to just be, what did we say sine theta was? Well, sine theta I think is going to be square root of x squared plus y squared over square root of x squared plus y squared plus z squared. So that is going to give us d theta equals del f del x. I don't know what it's going to be, but it is going to be a function. Del f, it's going to be a function of x, y, and z. Del f del y is also going to be a function of x, y, and z. Del f del z is also going to be a function of del x del y of x, y, and z. Yeah, it does look like over here he has derivative with respect to x. So really, yeah, I did all right because I'm not doing with respect to any particular variable because I can't. Because there's all three variables in there. But we've got this output from Mathematica, so I can see why that it does come out to give some kind of answer. What I'm curious about, though, because really, if this is the same, then these guys, the diagonal terms, are supposed to come out to be 0. And it doesn't look like they are 0. Let's play with a couple of them and see what happens. This one is xz r squared minus 1 over r squared, which would be not 0. And this one would be yz times r squared minus 1 over r to the fourth, which is also not 0. Now, I'm trying to come up with another reason that might have failed. Is it possible that I could have a commutativity error? What if I had this signs reversed? Would it give the same thing? This one goes r theta phi right and r theta phi coming down. And so r squared theta squared phi squared. But if I had reversed it so that it was, well, let's just check for commutativity errors. I'm going to come in here and just say transpose Jake dot Jake instead of Jake dot transpose Jake and see if that changes things significantly. Yes, it did. Okay, so we had a commutativity problem there. Goodness gracious. All right, so fantastic. That came out really nice. I'm happy. Okay, I've kind of crossed it out from before, but we can make that comparison now between these two forms. We got r squared here. We've got 1 over r squared here. Got r squared sine squared theta here. Got 1 over x squared plus y squared here, which is 1 over x cos x sine theta cos phi squared plus x sine theta sine phi, sorry, this is phi, I keep doing that, phi squared. And anyway, it does squared, which is, wait, x r, so this is equal to 1 over r squared sine squared theta, which is exactly what is the inverse of this. Okay, so what have we done? We have essentially confirmed this thing here, that the inverse metric of this is this. So now what does Wheeler say about these two things? He says there are more intrinsic ways to get this metric. Well, let's look at what he's literally done to get this metric. First of all, basically he's created a metric that is valid in 3 dimensions, dr, d theta, d phi, and he has crossed out that column, so it should be dx, dy, dz, and dx, dy, dz. He's canceled out this column here, and it would have been dr, d theta, d phi. And now he's done an inverse matrix, and I don't think it really makes sense. I'm not sure, because he's canceling out the dx, I don't think that the inverse metric here is really valid when you cross out that dx, but I'm not sure. We'll see how he uses it. I mean, what am I saying here? I'm just a little confused about what point he's trying to make by doing the inverse. He says there are more intrinsic ways to get this metric. One approach is to specify the symmetries. We require 3 independent rotations. I don't know. There are techniques for finding the general metric with given symmetry, so we can derive this form directly. Alternatively, we could ask for the 2-dim spaces of constant curvature, 2-dimensional spaces of constant curvature, computing the metric for a general 2 geometry, then imposing constant curvature gives a set of differential equations that will lead to this form. Well, I don't know about any of that, but I derived it by just leaving it in 3 dimensions and figuring out, you know, the Jacobians and putting them in the correct order. That was an important thing for me, because the first time I did it, I stuck those in the opposite direction, and that screwed everything up. But what it looks like to me is, in one form, we're basically just, once again, let me review this, because just kind of what I understand. dy dz. This is the length of the differential path element. Okay, so that's the length of the differential path element, and if we want to use dr d theta d phi, we need to use the Jacobian in here, so that we get it converted into del x, del y, del z. Let's just say that's going to the right, and del r theta phi going down. And then over here we have del r, del theta, del phi, and we have del x, y, z, Again, going down, del r theta phi going across, and this times this, dotted with this, will also give the length of the differential path up. Now, on the other hand, what does this give you? We're going to put del r, del theta, del phi going across, del x, del y, del z. Wait, I don't want all those del's in there, but okay. Del r theta phi going down, del x, y, z going across, and then we'll have dx, dy, dz there, dx, dy, dz going there. What does this give you? If you take the inverse of this thing as they suggested, so this is the description of that tangent plane, right? Because we're going to say dx equals 0 and just ignore that top thing there. Because these two Jacobians, when we multiplied those together, we'd end up with dx, dy, dz, and dx, dy, dz. And the only way we're going to eliminate this thing from it is if we say dx equals 0, and we allow dy and dz to change, and we would have dy, I don't even know what this will be, but it'll be 1 over r squared dy squared plus 1 over r sine theta squared dz squared. What does that equate to? I'm not sure. I know, but I think it has to be done with dx equals 0. Okay, I should stop predicting and read more of the paper and see what he uses this little submatrix for. Anyway, I'm going to stop there for now. Thanks for watching.